So I'll start the lecture. Thank you all for joining us. Good to see some faces in the audience that I know well. I'd like to talk today on circular economy, energy and environment. And it's very much about offshore wind and the environment and energy and how we integrate them all together. It's also about areas of the economy that are hard to decarbonize. So I hope you followed this and make some sense of it. The MaREI Centre has been in place since 2013, over 10 years. I've been the director since 2015. It's a large centre. We are graduating 200 PhD students. And from my perspective, 3 years of PhD, that's 600 years of work within the MaREI Centre. And it's very broad. So we have microbiologists, energy engineers, civil engineers, ecologists. We look at energy, we look at marine governance, we have lawyers, ecologists, and we look at fuels. One of the areas that I would work in would be very much in, I would talk about renewable hydrogen molecules. That's where my work is. So I'm very interested in H. I'll just check there in Teams. Is that working? Seems to be working. Admit all. So I'm the professor of civil engineering in UCC, and I'm the director of the MaREI Centre. And I work with these colleagues, so Arkisman Bose, David Wall, Richard O'Shea, Davis Rosmanis, lots of brilliant young researchers have informed the content of this lecture. So we've lots of narratives and lots of stories, and I suppose my role here tonight is to knit it all together. And this is the menu we work off. So we have this narrative that looks at renewable energy, that looks at anaerobic digestion, that looks at transport, that looks at agriculture, and we try to look at them all together in a system that utilizes energy and improves the environment. And last August, I spent a month locked away in a room working on this report for the International Energy Agency Technology Collaboration Program in Bioenergy. So it looks at integration of anaerobic digestion with power to X. So when we talk about power to X, we're talking about making things from electricity. And there's many things we can make, which I will talk about. So if I start on the top left and I look at renewable energy and electrolysers and look at it in an Irish context, and the one thing we do find about energy and environment, every country is different. It's bespoke. And Ireland is very challenged in that we're an island. So my electrical engineering colleagues often talk about islanded grids. We are one. We're not like Germany that's connected to France and connected to the Netherlands, or Denmark connected to Sweden and connected to Finland. We're very much an island. We have some interconnection, but it's quite sparse. So in the National Ocean Test Facility in Ringaskiddy, we have 3 large swimming pools, and we can test devices that are a scale of 1:20. So if we have a device that's 2 meters high, it could be 40 meters in the ocean. We can put down waves of 1 meter height, so they're 20 meter high. And we coordinate a lot of the ocean test facilities across Europe. But it allows us to look at various technologies such as floating offshore wind, which is seen as a technology of the future in Ireland. And this is what we're proposing to do in Ireland. We're already gone out to auction on the east coast for fixed bed offshore wind. And we go to the east coast first because it's shallow water. And then we go down where we are here in Cork. The next phase will be down here, a mixture of fixed and floating. And then we're going off into the open Atlantic. We're looking at going 65 kilometers offshore with floating offshore wind. Now, Ireland, because it's an island, has experienced the highest level of system non-synchronous penetration. And what that is the ratio of wind generation to the system demand. And we've gone over 75%. And this is great credit to EirGrid, but this hasn't come easy. For example, in Money Point, there's a flywheel that we spent 150 million euros to build to provide inertia. Because if everything is coming from wind, it's not like the old turbines and the old power plants. So an awful lot of work has been done to allow us have lots of wind energy on the system. And I suppose the challenge going forward is that we're only at 40% renewable electricity. What happens when it's 80 or 90% or 100%? It becomes very, very challenging. And we have a target of 5 gigawatts of offshore wind by 2030, and that takes us to 80%. So we're doubling our percentage of renewable electricity by putting 5 gigawatts of turbines in the water. And we talk about dispatch down. And again, this is very high in Ireland because we're an island. So all these wind turbines are blowing in the middle of the night in the summer. We're not using electricity. We spill or we dispatch. And this graph is from Davis Rosmanis in the audience. So Ireland is at, in 2020, 6 gigawatts of offshore wind, and we are dispatching down about 12% over the year. And that's either because there's a constraint on the electrical system or it's produced at the wrong time. So 12% of our electricity is very, very significant, and it's spilled. So there's an argument for hydrogen, and we will be producing lots of hydrogen. We make hydrogen by splitting the water molecule into hydrogen and oxygen. And hydrogen will then be an energy vector. It's a gas, which is very important. We actually, in Europe and in America, we use twice as much energy from the gas grid as the electricity grid. And gas is an ingredient, and that's important. So when we talk about natural gas, it's CH4. When we talk about hydrogen, it's H2. And the H is important because we make fertilizer from ammonia, NH3. So that comes from natural gas, and the N comes from nitrogen in the atmosphere in the Haber-Bosch process. We make methanol for chemicals, and that's CH3OH. At the moment, we use natural gas. In the future, that will have to be a renewable molecule. So natural gas is an ingredient that we hope will be displaced by hydrogen, which will come from offshore wind. So it's not just energy. There's chemicals, there's plastics, there's fertilizers, there's lots of things that use fossil fuel. And when we put fertilizer on the land, what we're really doing is putting natural gas on the land. So fertilizer comes from natural gas. If we don't have natural gas, where does the fertilizer come from? And anyone from a farming background would be well aware that the cost of agriculture escalated massively during the ongoing war with Russia because we didn't have natural gas coming across the border. We weren't making fertilizer to the same extent. When we talk about 15 megawatt offshore wind turbines, they're big. They're 340 meters tall. The Eiffel Tower is about 330. And we're going to put 7 gigawatts of offshore wind in the water. Originally, it was meant to be by 2030. That's 467 Eiffel Towers. So Ireland is going to put 467 Eiffel Towers in the ocean. Initially, it was meant to be by 2030. I'm a civil engineer. I'm thrilled because my graduates will be doing this. And we've been looking at ports. So we have to develop ports, which will be sort of almost like a radius of 500 meters. The ship comes in, picks up a 300-meter tower, picks up a nacelle, picks up rotors, and then goes out into the ocean. And when we're looking at some of these devices will be floating, so it's going to be hydrodynamics, there's going to be cables, we're going to be tying them down to the bed of the ocean. So civil engineers are going to be in high demand working on these very, very difficult systems. For example, in Foynes, in the west of Ireland, we're looking at wet storage. So there'll be huge frames sitting just inside the estuary, waiting for the 20 days when the waves aren't too high, and they'll all shoot out and try and erect these massive, massive structures. One of my graduates in 2012, his job was a method statement for getting a 15 megawatt turbine erected off Connemara in the wild West Atlantic. So it's very, very challenging for civil engineers, for process engineers, for electrical engineers. This is the auction pipeline. And what's interesting here, we have an auction pipeline out to 2030, and it's 17 gigawatts. Ireland's electrical capacity hasn't gone beyond roughly 6 gigawatts. So we're putting in a capacity that's 3 times our present capacity demand. And the idea is that we will do something with that power. And a perspective we would have is we'll make hydrogen. And from the hydrogen, we can make ammonia, fertilizer, or methanol for green chemistry and formaldehyde. So Ireland will have lots and lots and lots of energy significantly in advance of the maximum demand for electricity. Now, there will be periods of time where it gets very cold for 2 weeks and the wind isn't blowing, we will have problems. But typically, we'll have a lot more energy than is needed for electrification. This is quite nice. This is the south coast, so we're all sitting here in Cork. And these 2 zones, this is Marine Area Plan. Airgrid is the designer of the system, and they're looking at having substations here. But we're looking at a gigawatt coming ashore. And if I go back, so these little orange guys are non-grid. Initially, we were talking about hydrogen, but there are not enough electrolysers on planet Earth for Ireland to get this 2 gigawatts of electrolyser by 2030. So we're looking at a gigawatt, potentially, of power coming into Cork. And Cork City uses about 200, 250. So we're going to have a cable that does not go into the electrical infrastructure of Ireland that will have almost 4 times as much electricity as Cork needs. So that lends itself to, we can make hydrogen molecules and do things in Cork that will add value. Now, you could also say we'll export it into Europe. And from my perspective as a civil engineer, you can make steel in Indonesia, assemble it in UAE, put it in the water off Ireland, and have a cable into Europe. And Europe continues to make cars and gas and hydrogen and ammonia, and we watch it. Like, my preference is we bring it ashore and we do things with it and we make higher value and we export things with higher value. We had an ammonia production facility in the harbour in Cork. When we found natural gas, we made ammonia. Natural gas dried up. We stopped making ammonia, but the facility is still there. There's no reason we couldn't have green ammonia, where we use hydrogen from offshore wind instead of natural gas. But we did the same end product, ammonia. And there is a proposal now for an ammonia combustion facility in the harbour. So Mitsubishi have said that they're going to build an ammonia facility for combustion to make electricity. So when the wind isn't blowing for 20 days and it's really cold, we will have made ammonia, and that ammonia will make dispatchable electricity. We've looked at how this could work, and typically offshore wind farms will produce electricity when the demand is high. But in the middle of the night on a summer's day when nobody wants the electricity, the value will drop. The first auction in Ireland went out at about 8.5 cents a kilowatt hour for the electricity. So we're looking at bidding for electricity to make hydrogen at 4 cents a kilowatt hour in the day ahead market. And that would result in hydrogen at about 12 cents a kilowatt hour. So it's important to realize that if you have electricity and you convert it to hydrogen, the price of the hydrogen is about 3 times the price of the electricity per kilowatt hour, because there are inefficiencies along the way and there's infrastructure required. So hydrogen is more expensive than electricity. And if you were to go back then and make electricity from that hydrogen, so if you were to say, I'm going to store the hydrogen and convert that hydrogen back to electricity, you would be at about 22 cents a kilowatt hour. So you'd be almost 5 times more expensive than the electricity you came from. So the idea of hydrogen as a battery to make electricity later is very, very expensive. We also looked at where we put these electrolysers. So you could have a HVDC cable coming ashore. For example, we have a HVDC cable coming from Brittany into Cork, which is under construction. it's going to cost about 2 billion. If we were to start that process now, we'd be waiting for 5 years because of supply chain issues, and it would be more expensive. So 2 billion to come from France to Ireland. And we do see a lot of these wind farms in the future off the west coast being 65 kilometers from the shore. So there is a potential to put the electrolyser out on the wind turbine. So you now have your Eiffel Tower, you'd put it on a platform, you'd have a battery, you'd have a desalination unit, you'd have a Brittany discharge, and you'd have an electrolyser, and you can pipe the hydrogen ashore. So you can have a hydrogen pipe, which should not, we believe, take as long to order as a HVDC cable. You could also have, they like to have submersible, they like these spar turbines. If you have a 1 gigawatt farm, you could have 100 wind farms, 100 wind turbines, and they could connect to a floating factory. And on that factory, you'd have your battery, your desalination unit, your electrolyser. And we're looking potentially that you could have the Haber-Bosch process out there. So you could have ships coming up to this floating platform and loading up with ammonia, and it doesn't come ashore to Ireland at all. So this is plausible. I suppose we don't know, but there are lots of concepts, but there'll be very big floating factories off Ireland making electricity or hydrogen, or maybe making ammonia. Challenges for net zero. Methane. We probably need methane because we use an awful lot of methane at the moment. We're going to need methanol. We produce 110 million tons per year, and methanol is a precursor to formaldehyde, which brings us on to green chemistry. So we could have a green biopharmaceutical industry in Cork by making methanol. Ammonia, we mentioned this, it's a fertilizer, it's the most produced chemical on the planet. Again, the H3 can come from offshore wind. And then agriculture, it's responsible for 37% of our emissions in Ireland, predominantly from belching cattle, but also from storage of slurry. So I want to move a little bit, and I hope I'll bring us all back at the end. I want to look at anaerobic digestion and go into agriculture. So anaerobic digestion is a microbial process. It employs some bugs and archaea. We start off with complex polymers. There is a hydrolytic process. There's a fermentation process. You make lovely volatile fatty acids such as acetic acid and butyric acid, and you can convert those acids to methane and water and carbon dioxide. And there's lots of these across Germany, Sweden. They're very much a waste treatment process. I have some colleagues who don't like the idea of anaerobic digestion because it's bio and everything should be electrified, but we have waste products. We have slurries. We have food waste. My understanding is our food waste goes on a boat and leaves our island. So we could treat our food waste. And we've done an analysis that if you treated the food waste from Cork in a digester, you'd run the bus service. If you treated the food waste in Dublin, you'd run the bus service. So we can have a circular economy proximity principle, converting wet organic material to an energy vector. I led the IEA task on biogas for 6 years. We produced lots of reports. They're all available online. I've given 6 years of my life to this process. Lovely reports, lovely case stories, all available for free if you click on those links. But what's happening now, which I find quite interesting, Repower EU is Europe's way of looking at decarbonising, and they want a 10-fold increase in biomethane by 2030. The Climate Action Plan for Ireland wants us to have 5.7 terawatt hours of biomethane, which is 223 megawatt facilities. So we're going to be building really large anaerobic digesters to allow us to meet our renewable targets and to decarbonise. So I've just 3 little studies I brought in that I really like. My understanding is that Ireland has a target of 10% organic farms by 2030. I think Europe's target is 20%. And this is an organic farm that we visited in Denmark. And in this farm, there's no fertilizer, no synthetic materials. For weed killing, they have a tractor and they have 2 stretchers behind it, and people pick weeds. There's no fertilizer. But what they did is their dungs, they put them into a digester to mineralize them, to turn them into liquids and to have a nutrient value. So the only fertilizer on this farm is digestate from a biogas plant. So the biogas is almost secondary. They needed an organic fertilizer. They created an organic fertilizer, and they're certified as minus 0.82 kilograms CO2 per litre of milk. So it's an organic farm producing organic milk. There's no fertilizers, no weed killers, no natural gas spread on the land as ammonia. And this is the target for Europe and for Ireland that really can only be met by having small anaerobic digesters at these farms. This is the opposite. Denmark got together around 2010, and if you like, they had a farmers co-op, a farmers convention, and there was a lot of eutrophication, lots of pollution of water courses, and there was a decision made by 2030, slurry won't go onto the land raw. It will be treated in advance. By 2020, they had over 50% of the slurries are digested. And my understanding is there was grant aids for 6-month storage. So it was driven by water quality. We're aware that Lough Neagh in Ireland is highly polluted with a crust of microalgae from excessive nutrients. And Ireland has the 3rd highest level of bovinity on the planet. That's the ratio of cattle to people. We've lots of cattle and lots of slurry, and lots of our wells are contaminated. This is a solution. You have 6-month storage of slurries and you co-op together. So what happens here is that there is 725,000 tons of wet organic material in a digester at the center of this circle. And if you like, farmers will go to a sump, they drop in their slurry, it's augered up to 20 kilometers to the digester, biofertilizer is augered back, which has a high fertilizer value and saves in buying fossil fertilizer, and they put the gas into the gas grid. And this is a model. Very, very large digesters. You could have an anchor tenant, which could be food waste in Cork or stillage from a distillery. And Denmark is now at 39% of its natural gas comes from biomethane from these systems, but it was driven by water quality. Another thing that's quite interesting is CO2. CO2 is a product. Denmark uses 65,000 tons of CO2 per annum, and it goes into your bubbly water, into your beer. It's used, you can't slaughter animals without CO2. So you introduce animals to an environment with lots of CO2, they become dozy, and you can then slaughter them. This was an issue during Brexit. So a fertilizer plant closed down. We get our CO2 at the moment from the production of fertilizer. So we use natural gas, CH4, the H goes to ammonia, NH3, and the CO2 is given off. So that CO2 is collected, so it's fossil CO2 is used as the CO2 product in most countries. So when Brexit happened, a fertilizer plant shut down, there wasn't CO2, they couldn't slaughter pigs. Pigs got too old to be slaughtered, and there was mayhem. My understanding is there was money paid to the fertilizer plant to reopen. But this plant in Denmark produces on its own 25,000 tons of CO2. So the methane goes into the gas grid, the CO2 is left behind. There's a 7-step process to make it food grade. And CO2 is used in soft drinks, in dry ice, in cooling eggs, in laser cutting, in laboratories. It's a product. We need CO2. So we can get that CO2 from a biogas plant. And in Canada, they have this little bullfrog symbol. So when you buy drinks in Canada, if there's a bullfrog, it means it's a carbon neutral beverage, as opposed to a fossil fuel beverage. So typically your CO2 comes from ammonia production. So the joining together of offshore wind and hydrogen with anaerobic digestion is done in the next process, which I'll go through. So this is a plant we visited in Germany. It's Wörtel. It's the north of Germany. Lots of offshore wind, lots of curtailment of electricity. So what they did is they built a 6-megawatt electrolyser next to an existing anaerobic digester. It's a food waste digester. And the methane goes into the gas grid and the CO2 is left behind. So they made this electrolyser. Electricity that would have been curtailed is spilled to the electrolyser. And we have the Sabatier equation, which is 4 moles of hydrogen from the offshore wind, 1 mole of CO2, from the biogas plant gives you a mole of methane and water. So here they have biomethane going into the gas grid, but they also have what they call e-methane. So that methane comes from the hydrogen from offshore wind that would have been spilled and the CO2 that was a byproduct of the biomethane facility. And they ran 1,000 Audi natural gas cars. So the business model was you buy your car, you pay a certain amount a month, and you have a little credit card that is your fuel, and that fuel is e-gas. So we found that very interesting, and we're biological engineers. So we came back, and this is the work we do. We do a lot of work here, but this guy is a hydrogenotrophic methanogenic archaea. What he does is the archaea eats hydrogen and CO2 and produces methane. So it's exactly the same as the Sabatier equation. The Sabatier process here operates at 400 degrees Celsius. It's a chemical process. This is a biological process, and it's very favorable. So when you look at the stoichiometry, it's a negative Gibbs free energy, which means it's favorable. So we went into our lab and we started adding hydrogen and carbon dioxide to our anaerobic broth. And we found that all of a sudden this became dominated by hydrogenotrophic methanogenic archaea by the name of Methanothermobacter wolffi. And wolffi is the Latin for tungsten. So giving them a little bit of tungsten, they worked a little bit better. So we found a little archaea that ate hydrogen and CO2 and gave us over 95% methane. So we then decided, well, we have to go further. And we did lots of science, and this is Davis Romanis's PhD. We looked at feeding hydrogen into an anaerobic reactor, hydrogen and CO2. Hydrogen doesn't go into solution very readily. We needed it under pressure. We needed microbubbles. And we played with the lots of system. And so there's 3 years of work here by Davis Romanis. And we ended up with this type of a system. So we decided what would work quite well is add hydrogen and carbon dioxide under pressure, circulate the gas a few times, do some of the job, go on to the second reactor, do a bit more, go on to the third reactor, and we have quite a good system. We then designed a bigger system. This is the exact same, except it's bigger. So we've stage 1, stage 2, stage 3, and here we have stage 1, stage 2, stage 3. So we're adding hydrogen carbon dioxide under pressure in solution around a few times. Retention time is about 6 hours. And we found that this is the first reactor, the second reactor, the third reactor. But the third reactor, we were getting over 97% methane. So it works. And it works in a continuous process. And we did it at a big scale that you could assess and examine. So we have a nice technology. And we call that TRL level 633. So it needs a lot of work. You need to go into the field and do it. So we were looking then at how this would work, and we have colleagues in Germany, and they were also playing with this technology. So here is the little ex situ biomethanation and an electrolyzer. So this is a demonstration plant. It's sort of research. So electrolysis is water being split into hydrogen and oxygen. Hydrogen has a heating value of 3 kilowatt hours per meter cubed. They put in a 300 kilowatt electrolyzer. At 60% efficiency, there's 180 kilowatt hours of hydrogen per hour. Hydrogen is 3 kilowatt hours a meter cubed. So they're making 60 meters cubed of hydrogen per hour. We need 4 times less that amount of CO2. So the biogas plant is 14 meters cubed of CO2. So 4H2 plus CO2 is CH4. So the biogas, which was 16 meters cubed of methane and 14 meters cubed of carbon dioxide, is now 30 meters cubed of methane. So we've converted all the CO2 to methane. We've upgraded the biogas to pure methane. We've increased the energy output by 67%. There's another plant in Copenhagen, Biocat. It's a bit bigger. You have a 1 megawatt electrolyzer. We have 600 kilowatt hours of hydrogen. That's 200 meters cubed of hydrogen, which will react with the 50 meters cubed of CO2 to make it methane. So our hydrogen is converting CO2 to pure methane. The biogas becomes pure methane, and we've increased the yield by 67%. So that's early technology. So we're trying to see power to X. When we talk about power to X, when X is equal to 1, it's hydrogen. When X is equal to 2, it's methane. When X is equal to 3, it's methanol. So we go to a liquid fuel. So there's all these X's. So we've looked at hydrogen with an electrolyzer. We've looked at methane with ex situ biomethanation. So we're trying to see where would we do this? Why would you do it? And this is a piece of work we did with Davis. And the idea behind this was we love to object to planning in Ireland. It's a pastime. We'll object to things. A digester was proposed in my community, and my neighbours were saying we'll wake up dead in our beds in the morning because we'll have asphyxiated. So we love to object. So we looked at this in terms of, if you did an electrolyser in Cork, where would you put it? I designed Cork main drainage sewerage scheme in 1992. I've never been there. So people don't go to wastewater treatment plants. So instead, we'll stick the electrolyser in Cork main drainage down in Carrigrenan. And we sized it based on the wastewater treatment plant. So typically you pump air into a wastewater treatment plant. Air is about 20% oxygen. So if you pump oxygen, you reduce the pumping by a factor of 5. So we worked out the oxygen demand, and we figured out what size of electrolyzer we'd require to supply that oxygen, and it was a 10 megawatt electrolyzer. And 10 megawatt is sort of the standard for electrolyzers. And that would deal with the curtailment of 18 8 megawatt turbines. And it would also produce about 14 million meters cubed of hydrogen. We looked at the existing sludge digester, so they digest primary sludge and waste activated sludge, and we would need 20% of the hydrogen to convert that biogas to pure methane. 80% of the hydrogen would be left behind, and we could do whatever we want with that hydrogen. So we looked at, just for transport, we looked at biomethane truck and a hydrogen truck, and we could run 400 trucks on methane or hydrogen. So that was an example of what we could do. At the moment, this is biogas, and the usage isn't that varied, so we could do lots more things. We could put that methane directly into the gas grid. We could do lots of things, but we decided to look at transport case. The other thing we were looking at is there's lots of anaerobic digesters in Germany and Denmark, and we're going to have more electricity than we need, so we can make hydrogen at those biogas plants. So what we looked at, this is Denmark. They had lots of anaerobic digestion, big digesters dealing with slaughter waste. They don't, one thing I'd like to say is they don't use crops. So Denmark does not have crops, because one of the criticisms of anaerobic digestion is we'll use food to make gas. So Denmark decided that there's no crops. This is for food waste, for pig slurry, for slaughter waste. And at the moment, the level of biogas production is a 39% substitution of natural gas. But by putting an electrolyzer and an ex situ biomethanation at one of these digesters, you increase the output of methane by 67%, because all that CO2, which is about 40% of the biogas, becomes methane. Ole Helvepund is the CEO of Nature Energy. They've been bought out by Shell, but they're now building the world's largest ex situ biomethanation system. And the plan is, if they do that at every digester, without using any more feedstock, you're at 65% green gas. So that's a plan. And they will have 100% green gas by 2030. So all the gas in the grid will be green. Some of it will be biogenic from slaughter waste and distilleries. Some of it will be e-methane. Hydrogen is very, very voluminous. It's quite explosive. So converting it to methane condenses it, and you can use an existing infrastructure. So the gas grid that's there can use methane to transport it. It can't use hydrogen. We then looked at other technologies which are quite nice. So this is a typical anaerobic digester. This is power to gas, where we add hydrogen, but we also looked at just put the electrodes directly into the anaerobic digester, because an electrolyzer is at best 70% efficiency. So we stuck electrodes into our digester. And what happens is electrons go to the cathode. The electrons react with CO2, and they convert the CO2 to methane. So if you like, this is power to gas in one chamber with no electrolyzer. We put in a voltage of 1 volt. And we found that we were getting 6 times return of methane compared to the electricity we put into the digester. So it's at a very low TRL, but this is a way of almost halving the feedstock to get the same amount of methane output. So we call that a bioelectric scheme. Or one thing we're doing, which I'm really fond of, this is for small scale systems. So we're introducing algae. And we've been working on this for a while, and it's the PhD of Arkisman Bose, who's now a full-time lecturer in process engineering here in UCC, funded by Eli Lilly. But the work we did was, is there a way of upgrading small-scale biogas? So we're looking at Dingle, and we've done this work with Dingle Hub. We've been going down there since probably 2016. But they had a problem set, and I love this. So the problem set they had in Dingle was they would like to have a slow food movement. They'd like to say this is Dingle beef, grown in Dingle Peninsula, and it's salty because it's on a peninsula, and you'll pay €2 extra because it's Dingle beef. The problem is they don't have an abattoir, and the prices they were quoted for dealing with byproducts was very, very high. So if we build a digester in Dingle, they can have an abattoir, and the byproducts in the abattoir goes into the digester. They also spend $2 million a year on food waste going from Dingle restaurants to Waterford to be composted. So they save $2 million by having a digester because the food waste goes into that digester. They spend $1 million a year on diesel in Dingle for tractors, and they want us to make methane for their tractors. So what we're looking at is that the biogas goes up through a carbonate bicarbonate tower. We get a pH of around 11 or 12. The CO2 becomes bicarbonate, but we introduce microalgae, and the microalgae take out the CO2 and is a superfood. And you buy microalgae for about €4 for 40 grams. It's about €10,000 a ton. So at home, my wife makes microalgae smoothies with cacao, but they're meant to be full of fabulous things, and some of my family are vegetarian, so it's a way of getting good food into them. So we could be growing microalgae, and your money comes from microalgae. So your biogas comes almost irrelevant. You're making money from selling microalgae, which is taking the CO2 out of the biogas plant, which leaves Dingle have an abattoir, which reduces Dingle's costs in terms of food waste. And also Dingle is now driving their tractors on methane, and they've also got a biofertilizer instead of a mineral fertilizer. So they can have organic farms and get even higher value. So you could have organic slow food from Dingle and microalgae and biofertilizer. And this was done by engaging with the community. One thing I'm not happy with is the way that the farming community is sort of is pillared as the worst of all things. I mean, we need to sit down with the farming community and plan, like, how can farming be sustainable and allow wealth in the community. So we talk about having GA teams. If you have this in Dingle, you have young people staying there, getting PhDs, producing microalgae and playing GA. So we don't depopulate Dingle or Kilkenny or rural areas. We have another product for them, which is sort of a biorefinery system. We've done a lot of work on marginal abatement costs because previously a report was done by McKinsey that said that biogas cost €300 a ton, and it was outside the climate action plan. But if you're selling microalgae and biofertilizer and CO2, we can actually craft that it's a negative. It's paid for by the microalgae. So it's not expensive if you have a biorefinery multi-product type system. I just want to jump on a little bit. When we're looking at the hard decarbonized sectors, we're looking at shipping, we're looking at aviation. So if Ireland wants to be net zero and we leave this island, we're going to get on a plane that will burn a fuel, or we'll get on a ship that burns a fuel. So we looked at fuels and power systems, and this is the NADAR. This is where you don't want to be. And this is a lithium-ion battery. It's very heavy. It takes up a lot of space. It's fine in a car. Well, it's not fine in a car because I'm a structural engineer, and all our high-rise garages aren't going to work in the future because EVs are far heavier than internal combustion engines. So our high-rise car parks are in trouble because they're heavy. But generally they're fine, except for high-rise car parks. But when you start looking at a jet, you can't put a battery on a jet and go to Dubai. So it's going to be either jet fuel or something that's green, such as methanol to gasoline. So if we make e-methanol, we can run a plane on it, or Fischer-Tropsch diesel. But it's going to be liquid. And the same for shipping. So we want to be up here. This is utopia, really light, takes up no space, loads of energy. So I suppose the thesis here is batteries are great for cars, not for ships, not for planes, and we're going to have green chemistry to make green liquid fuels that are dense. We looked at the electricity for a truck. So this is a truck. And we found that for less than 450 kilometers, you can put a battery in a truck. Beyond 450 kilometers, the truck is bringing the battery around the countryside, and you can't put anything else in there. So we reckon a hydrogen fuel cell. The problem with a hydrogen fuel cell, it takes about 3 times the electricity to make the hydrogen, to compress, to put in the truck than a battery. So a battery is great in terms of efficiency from electricity to propulsion, but it's too big, takes up too much space, it's too heavy. Another thing we've looked at, again, it's very nice. This is in Linköping, up in Sweden. I go up there a lot. I have great friends up there, but they have a slaughter facility, and it was causing pollution to water courses. So they built a digester to improve water quality. They used the biomethane to run the bus service to improve air quality. So that was going quite well. It's been there since the 90s. They then moved into trucks. So they now have liquefied biomethane. So you drop the temperature to about 200 degrees Celsius, minus 200 degrees Celsius, and your hydrogen turns into liquid. And these trucks are traveling 1,000 kilometers on one fill. So we can use waste products, food waste, pig slurries, distillery waste to run trucks 1,000 kilometers in a circular economy system. And one thing we're also looking at is that digester in Linköping. If we put an electrolyser at it, we can improve the fuel production by 67%. So rather than methane going in the truck liquefied and CO2 going to the atmosphere, we capture the CO2, we react with hydrogen from offshore wind, we make more methane, and the truck goes further. And a battery is not suitable. I mean, these trucks will never run on a battery. It'll either be a hydrogen fuel cell or some form of renewable diesel. We did a lot of work then in distilleries, and this sort of shows the circular effect. So we looked at a distillery in Austria, the Gosser Brewery, and this brought us to Middleton, Irish Distillers Limited, Pernod Ricard. So we've had a number of projects with Pernod Ricard within the MaREI Centre, and the manager, the energy manager, is one of our graduates, James Brown. So we looked at 21 decarbonisation pathways for the distillery, looking at electrification, organic Rankine cycle. Now, Middleton is relatively suburban, rural. The electrical infrastructure isn't there at the future. It could be brought down there. But whatever we did, we couldn't get beyond 67% greenhouse gas saving. So if we electrified everything, there's still going to be emissions. You've got grain growing in the field, you've fertilizer on the grain, you've tractors coming from the field into the factory. So we looked at a number of processes. We did a multi-criteria decision analysis to see what they wanted, but they're now spending 50 million on a digester in Middleton, and the biogas will take away natural gas that's used to evaporate stillage of alcohol. And this is where it's interesting. Scope 1 emission is natural gas burned in the distillery. Natural gas in the old days was about 3 cents a kilowatt hour. We could also use the biomethane in the trucks that go out to the fields, and that would get us 15 cents a kilowatt hour in replacement of diesel, but that's scope 3. So we got more money from scope 3, less money from scope 1, but scope 1 is more important than scope 3. And we also found that the fertilizer from the digester would replace the fossil fertilizer on the land that grew the grain. So again, you've got this circular economy system, which is quite nice. It's a proximity principle. It's, in effect, the distillery will rely on the distillery for its energy, for its fertilizer, and will become carbon neutral. Methanol. We have a project on methanol, and methanol is interesting for a number of reasons. One, formaldehyde comes from methanol, and green chemistry comes from green formaldehyde. Shipping is going to run on methanol. It's a done deal. So new ships which will run on decarbonised fuel will run on methanol. Maersk have 17 methanol ships, and they wanted green methanol, and they found it hard to find. They eventually went to Denmark, and they're steam methane reforming biomethane. So the biomethane in Denmark, which is CH4, if you add an oxygen molecule, your CH4 becomes methanol, which is sometimes called wood alcohol. It's the smallest of the alcohols. So it's very easy to convert methane to methanol. So they're going to steam methane reform biomethane for shipping fuel. So we were looking at potentially in Cork, we're going to have this gigawatt of offshore wind coming ashore. We convert it to hydrogen and we capture biogenic CO2. And the joy of the distillery is that Irish distillers have 55,000 tons of CO2 from the fermentation process. They're building a 16 megawatt digester. They're actually increasing the distillery. So we reckon there'll be 120,000 tons of biogenic CO2. So this CO2 cannot come from coal. It cannot come from natural gas. It has to be a biogenic CO2. So we reckon, in particular, Irish distillers, 120,000 tons of CO2 will react with the hydrogen from offshore wind, and you'll make methanol. And that methanol can be a shipping fuel or can be the source of green chemistry. So I would say, and it's something my colleague Brian Gallagher always said, like energy is more than electricity. I suppose what I would say is decarbonisation is more than energy. There's fertilizers, there's cattle, there's slurries, there's chemistry. This is a pilot scale green ammonia production facility. So again, offshore wind is your H, N is the Haber-Bosch process, and you make green fertilizer. I have a colleague in Italy who did a very interesting study. So they make methanol in Italy, they make ammonia in Italy. His idea was they would build 100 biomethane plants and they would sell the biomethane virtually to the existing fossil fuel plants. So in essence, the fertilizer plant keeps going, but they're paying the biomethane plant for their renewable green biomethane molecules, and there's a guarantee of origin. And that is a process. But our preference is that it's proximity. Our preference is that this is an electrolyzer taking hydrogen, grabbing in, and it's a new green facility, because they would be accused of greenwashing. I mean, if an existing fertilizer plant said, we're now green because we bought molecules, people would say you're greenwashing, even though there's a process where these biomethane plants. And one thing that's interesting, the IRA, the Inflation Reduction Act in America, with hydrogen, they're saying there's 3 pillars. So if you make hydrogen, it has to come from new facilities. It's called additionality. So you have to build a brand new wind farm to make your hydrogen. It can't be an existing one. They also have regionality. So it can't be a wind farm in Canada. It has to be a wind farm in America on your grid. So we've got additionality, regionality, and also by the hour. You have to figure out what's produced by the hour, and that's the hydrogen you can make. So I would say, again, for this type of a system, we could employ those 3 pillars. It's a brand new wind turbine. It's producing hydrogen. We're budgeting by the hour, and that's the fertilizer that we produce. Green steel. Steel is a horrible process. We had Irish Steel. I actually worked in Irish Steel when they were bought by an Indian consortium. And we worked out all the liabilities and we worked out all the costs. And I think Irish Steel sold to ISPAC for a cent. So I'm one of the reasons it was a cent, because I looked at all the liabilities in Irish Steel. But we could now make this with hydrogen. So we could use offshore wind to make hydrogen, to make steel, to go back out and be offshore wind. But at the moment, all the steel we'll be putting out there is coming from coke, which is a horrible process. So again, decarbonisation is more than electricity, it's more than energy, it's more than fertilizer, it's steel, it's everything we do. Power to food, this is the new one, which I find fascinating. So I mentioned microalgae as a sort of a superfood. It could be, one thing I find interesting in terms of ethics is that some people don't like biogas because it's part of agriculture and therefore it's part of the meat industry. So we could make microalgae from a biogas plant that's been fed slurry, and the microalgae is vegan, but maybe it's not vegan because it came from a cow. But then if it came from whiskey and you'd whiskey byproducts, would it then be a vegan product? So there's lots of ethical questions in what are we doing and why are we doing it? But this is a nice one. We've done a lot of work in volatile fatty acids and biorefinery. And this is from, we do a lot of work with whiskey byproducts. So we've been looking at making chemicals or volatile fatty acids. And depending on the loading rate, we can get capriotic acid, or we can get propionic acid or acetic acid. We can vary the outputs. So we can make chemicals from byproducts of a distillery But what that then does, and this is SUSFIRM, this is led by John Morrissey, but it's very interesting. So offshore wind, hydrogen, fermentation of byproducts, you end up with acetate, and acetate will be a source of future food. So we will make proteins from offshore wind, biogenic CO2, and this is, if you like, in competition with cattle. Now, my understanding is Italy has banned this already. Italy has said, you're not touching our food. But this is going to happen. So we will make proteins from energy and biogenic CO2. So now we have power to food, power to fertilizer, power to chemicals, power to hydrogen. So it's a huge world. It's really, really interesting, I think. So this is our system, and there's lots of other things in there that I haven't got into. Pyrolysis is a fabulous. We can make from digestate pure carbon. That carbon can go back in the soil. It takes 100 years to make 5 mil of soil. So what we're looking at is when we digest something, we can pyrolyze it, make pure carbon, and put it back on the soil and make the soil richer, which increases photosynthesis, which increases yields. So I would say it's a fabulous world out there. There's loads of things we can do, and it's about how we do them and do we do the right thing. But I would say there's no silver bullets. Like offshore wind on its own or PV on its own isn't going to solve our problems. We have lots of problem sets to get to net zero. So again, I'd just like to thank the team. I think Davis is here, one of my PhD graduates, but this is the work we do over the last 7 or 8 years. And thank you for your time. And I'll take any questions.